So before we get started, the first question that we need to ask is, what is a linear regression problem? In a regression problem, we have a set of inputs x and we want to predict a real valued output quantity y. The inputs are also called features, covariates, independent variables, predictors, etc. We can classify linear regression based on the number of input and output variables. Simple linear regression is the simplest case with only one input and one output. It is also straightforward to visualize simple linear regression, which we will see soon. Multiple linear regression takes in more than one input to produce one output. To predict the output y, we need a mathematical function that takes the set of inputs and spits out a prediction. This function is also known as the regression function. From a probability standpoint, the regression function is the expected value of y given the set of inputs x. We have so many different functions to choose from. In the case of linear regression, the prediction function is a polynomial of degree 0 or 1. It has the form f of x, where x is the set of inputs from x1 to xp is equal to beta naught plus beta 1 x1 plus beta 2 x2 so on till beta p xp, where p is the number of inputs and the betas are the coefficients or the parameters of this model. Linear regression is the process of determining these coefficients so that they best fit our data set. Linear regression model is designed to work with structured tabular data. So you can think of it like whenever you have a data set that looks like a spreadsheet table, you can use linear regression to make predictions based on the columns which are the inputs to the model. Before we get into the math and solve the linear regression problem, let's visualize simple linear regression and try to get some intuition. You have a data set with one input variable x1 and one output variable y. We can easily plot the different observations on a xy plane. Our regression function f of x is equal to beta naught plus beta 1 x1. Linear regression fits a line through these data points. The green line is our prediction line. The whole linear regression process is a systematic way to find this prediction line. For now, let us assume we already have the best fit line. There are two parameters in this model, beta naught and beta 1. Beta naught controls the line's y-intercept and beta 1 is the slope of the line. You can use this line to make prediction y hat for a new unseen input x. If we have one input, linear regression fits a line, and if we have two inputs, linear regression fits a 2D plane, and you see the pattern. You can extrapolate this idea to multiple inputs. There is another way to think about linear regression. You can think of the output y as the weighted sum of inputs, where the coefficients are the weights. Higher the weight of a particular input, more it impacts the output. This in some sense tells us about the importance of a particular feature or input. In the next step, we will formally write down the mathematical model of linear regression before moving to solving it. There are two ways to write down the equations for our model, and I will show you both of them side by side. The ith predicted value y hat of I is equal to f of xi, which is equal to beta naught plus weighted sum of all the input features. Beta naught is the bias and all other betas are the weights. Here I stands for the ith observation or the row index, and j is the jth feature or the column index. We can further rewrite this equation by absorbing the beta naught into the summation by setting xi0 equal to 1. xi0 is a dummy feature that we have introduced to make the summation look more concise. Now we write the system of equations using the matrix notation. Here x is n cross p plus 1 matrix, where n is the number of observations and p is the number of features. First column is all ones because we have set xi0 equal to 1. The prediction y hat is equal to matrix x times the beta vector. Whenever we fit a statistical model, we need a metric to quantify its performance, and then we optimize that metric to obtain the best fit model. So we define an error function, also known as the residual. The error for a given input x is the difference between the actual output from the training data and the output predicted by the model. It does not matter if the error is positive or negative, so we take the square of the error to remove the sign. RSS is the residual sum of squares and MSE is the mean of the squared errors. We take the mean by dividing RSS by number of observations, which is n. We need some background about 2 norm of an n-dimensional vector x. 2 norm of the vector x is equal to square root of x1 squared plus x2 squared so on until xn squared. If you carefully look, 2 norm squared of a vector can also be written as x transpose times x. Now that we have learnt about 2 norm of a vector, we can use this knowledge to represent the residual sum of squares using the 2 norm. RSS of beta is nothing but the 2 norm squared of the difference between the vector y and y hat. This is equal to y minus x times beta whole transpose times y minus x times beta. We are getting closer to the solution. Now that we have a proper error metric to quantify the error in our predictions, we want to minimize it. How do we minimize it? We first differentiate RSS of beta with respect to beta and then equate it to 0. Then we rearrange the terms to solve for beta. After doing that, we get beta is equal to x transpose times x whole inverse times x transpose times y. The prediction y hat is equal to x times beta. The vectors in matrix X span a subspace known as the column space of X. I also want to remind you that if two vectors are orthogonal, their dot product is 0. If you look at equation number 3, then the term y minus x beta is the error vector, and this equation tells us that we find betas in such a way that the error vector is orthogonal to the column space of X. And if you look at equation 7, this equation tells us that the prediction y is obtained by projecting the vector y onto the column space of X. In equation 7, the term highlighted in yellow, x times x transpose times x whole inverse times x transpose is the projection matrix. You probably may not understand some of these details because it requires a strong understanding of linear algebra. But I'll try my best to explain these concepts through a concrete example. Consider this toy dataset with 3 observations, 2 features and 1 output. Step 1 is we write down the system of linear equations. We can consider the feature columns as vectors and plot them on a 3D space. The orange color vectors correspond to the feature columns in our dataset. The blue color vector is the actual ground truth y value. The vectors in orange feature matrix span a subspace in this 3D coordinate space. Span is obtained by taking all linear combinations of the feature vector. Next, step 2. Most often we will not have an exact solution for the equations, so we solve them by minimizing the errors and obtaining the best beta values. Step 3. We can use these beta values to make a prediction and calculate the error vector. This error vector, if you plot it on the 3D space, is perpendicular to the column space of the feature matrix. There is a caveat to using the closed form solution that we obtain for linear regression. What if the inverse of x transpose x does not exist? Before I give you the solution to this issue, first let us understand when this inverse will not exist. First thing, keep in mind that x transpose x is always a square matrix. X transpose x will not be invertible when the columns of x are dependent. Here are 2 examples where the columns of x are dependent. In the first example, the second column is 2 times the first column. In the second example, the fourth column is the sum of second column and 2 times the third column. Such matrices are called singular matrix. The solution to this problem is to take the pseudo inverse of x transpose x. Pin is the MATLAB command to take pseudo inverse. I am not going into the details of how to take pseudo inverse of a matrix. That is beyond the scope of this video. Maybe I'll make another video in the future explaining the pseudo inverse. Thank you for watching this video. I wish to make more videos like this in the future. If you like this video, please don't forget to like and subscribe. It will tremendously encourage me to create more content like this. Thanks.